Okay, it's 9 a.m. and we can start. So first of all, before we start, this homework, current homework is due Wednesday. And again, it's a long weekend. And on Tuesday, as far as I remember, on Tuesday, will be Monday's schedule. Right? So we're not going to have a lecture on Tuesday. Right? So we're going to have, most of you are going to have recitation classes. So just look carefully at the schedule. Okay, so that's short announcement. And now back to our material. So the main goal of today's class will be its time. Because you remember we're moving towards simple circuits. Now we need to introduce the idea of the current, right? But before we start doing that, we have one slide which we haven't finished in the previous lecture. Right, you remember we started developing a method of an equivalent capacitance, right? We derived the formulas for the case and pieces of physics for the case for a case when capacitors are connected in parallel, but we did not discuss a case when capacitors connected in series. So let's do it. Although we practiced already in our recitation classes how to analyze circuits, but still, since there are plenty of important physics in that derivation, so that's why I cannot convince myself to skip that derivation. It's barely a derivation. It's basically discussion of physics. Okay, so now, and then after that, we will go into this idea of current. Okay, as I said, so capacitors connected in series. Again, the whole idea of this method is if capacitors are connected in series, either in series or in parallel, we can introduce, instead of a real circuit, we can introduce an equivalent circuit where these capacitors are replaced with a single capacitor, which we call an equivalent capacitor, right? And circuit and equivalent circuit. And very important words we have to add every time. When we do this replacement, the rest of the circuit, in this case, is just a battery, but in general, it can be more complicated circuit, right? The rest of the circuit must work in exactly the same way in an equivalent circuit over here and in the real circuit. So if potential difference delta V here, delta V must be there. If charge Q is taken from this battery, exactly the same charge must be taken from that battery, right? So we must not disturb the rest of the circuit, right, with these manipulations, right? Okay, and now, again, we analyze capacitors. And you remember that circuit Trinity, which I told you about in the previous class. So whenever you analyze a capacitor, you have to think about three parameters: C, Q, delta V. Capacitance, charge, the potential difference, right? So, and we're going to do it the same. We're going to do it again. Just analyze those three parameters. So first of all, we need to derive the formula which can be used to find C equivalent. So C will be used at the very end, capacitance. So then we have only two left. Q, two parameters, Q and delta V, charge and the potential difference. And I'm asking, so which quantity out of those two, Q and delta V, which quantity is the same for all these three capacitors? Usually I ask, and sometimes, okay, quite often, students tell me the right answer, right? But when I ask about justification, in that case, right, so justification is more complicated, right? So usually students tell me, yes, charge is going to be the same in all these three capacitors. Charge. Let's justify why charge is going to be the same. Okay, in order to do that, let's just look carefully at this part of the circuit. You see this reddish rectangular, this dashed red line. So let's look at this part of the circuit, which looks like an H, capital H, right? What can we say about this part of the circuit from the point of view of an electron or electrons? From the point of view of electrons, look, for electrons, what is this between these two electrodes, right? You see, between these two electrodes, it's a gap, either vacuum or a dielectric material, which electrons cannot jump over. Of course, there are no quantum mechanical effects, right? Quantum mechanical effects happens over very, very short distances. These distances are gigantic. Somebody's mic is on. Okay, yes. Okay, thank you. All right. So for electrons, this gap, this distance is gigantic. It's almost like an abysmal abyss. Then, from this side, this gap, again, it's a gap. Electrons cannot get through this. So effectively, from the point of view of an electron or electrons, this part of the circuit is an island. Okay. It's an island which cannot be reached by electrons from the circuit, and from which electrons cannot escape. So it's a completely isolated island in the middle of the ocean. And moreover, what can you say about the charge in this island, the total net charge of that island? It must be an electrically neutral. Because when there is no current, let's say you have a switch originally, right? So let's say the switch is open, right? So what will be the charge in the whole circuit and in that island? The whole circuit will be electrically neutral and the island will be electrically neutral. And when you close the switch, charge will appear in the rest of the circuit, but not in that island, because electrons cannot get on that island. So that island is going to be electrically neutral, completely isolated and electrically neutral. Amazing, right? So now, once we establish that, now let's assume that some amount of charge left this positive electrode, right? Let's assume that we close the switch, and now let's say this amount of charge Q left. How far will this charge be able to go? Not that far. They will come to this electrode, right? And that's it. It's a dead end. They will just gather over there, right, all these positive charges, right? So over here, this electrode will be charged with plus Q. Because they cannot jump over that gap, and they cannot get on that island. Okay, so this electrode will be positively charged with charge plus Q. Okay, so now, what will be the response of electrons on this island? They see that over here, there are positive charges, and of course, electrons feel attracted to positive charges. Of course, plenty of these electrons will run towards this positive charge. But again, they cannot get through this gap, and of course, as a result, all those electrons will gather on this side of the island, on this electrode of this island. All right. And what will be the amount of charge? That amount of charge which will be accumulated over here, minus Q. The same like this, but opposite inside. Basically, it's a charge induction, which we discussed in the first lecture of this semester, charge induction. Right? Because still, these capacitors, electrodes of this capacitor, they may be a millimeter the distance, right? Yeah, it's still gigantic for electrons, but you can easily induce charge on that electrode. And the total charge induced on the opposite electrode, on this electrode, will be exactly the same as this, but negative. Right? So as a result, on this side of the island will be negatively charged. But again, the whole island is still electrically neutral, because no one can come and no one can go from that island. So it means that if we have negative charge Q, there must be positive charges left behind on this side of the island, plus Q. So overall, electrically neutral. Okay, so that's what happens on this island. Now, this part of the circuit, again, it's an island in exactly the same situation like this one. Exactly the same. So gap here, gap there, that is an island in the middle of the ocean. Again, the same similar response. These electrons see positive charges on this side. Negative charges, electrons will come to this electrode. So that electrode will be negatively charged with minus Q. And again, this second island, again electrically neutral. So this electrode will be charged positively, plus Q. Okay, now this electrode is physically connected to the battery. So electrons can actually run over here and charge that electrode. It will be minus Q. So now you see in this capacitor charge Q, in this capacitor charge Q, in this capacitor charge Q. All these three capacitors have exactly the same amount of charge Q. So that's justification why when capacitors are connected in series, the amount of charge in each of those capacitors is exactly the same. All right. Okay, so now again, three parameters, back to three parameters. So C will be at the end, Q we discussed equal, Q's are equal, and then after this we will have to discuss potential difference. But let's summarize charges. So Q's, all these Q's are the same, Q1, Q2, Q3 the same, and equals to the charge taken from the battery. But like in the previous slide, at the end of the previous lecture, now let's connect these results with the amount of charge in the equivalent capacitor, which in order to get a very important piece of physics. Look, you remember, when we make this replacement and introduce C equivalent, the rest of the circuit must work in exactly the same way. I kept reminding you about that. So it means that if charge Q, this charge Q, right, is taken from the battery in this circuit, it means that exactly the same amount of charge must be taken from that battery here. And where does this charge go? Not much of an option, just there is only one charge, there is only one capacitor. So all this charge will go to that capacitor. So it means that in that equivalent capacitor, the amount of charge will be equal Q. Right? Okay, let me label it as Q equivalent to emphasize, right? So it means that this Q equivalent equals to this charge Q equals to this, and this equals to the charges over here. It means that charge in the equivalent capacitor equals to charges in capacitors connected in series. It's a very important piece of physics which we've already used in our recitation classes because we analyzed problems like this. All right. So you remember at the end of the previous lecture, what was the same for capacitors connected in parallel? Potential difference. Potential difference in equivalent capacitor was equal to potential differences across capacitors connected in parallel. Now it's a charge. Charge in an equivalent capacitor equals to charges in capacitors connected in series. So very important pieces of physics. And because of these pieces of physics, most likely I will never skip these derivations. Because again, it's barely a derivation. We discuss physics, what is physics happening in these circuits. Right. Okay, so now once we establish this, but again, it doesn't give us an equation. It's a very important piece of information, but we need an equation in order to find the formula which can be used to find C equivalent. And that can be found from delta V's, the last parameter out of that circuit trinity, CQ delta V. Okay, so what about delta V? It's obvious. Delta V across the whole circuit provided by this battery, delta V, equals to the sum of potential difference across the first capacitor, delta V1, plus potential difference across the second capacitor, plus potential difference across the third capacitor. Right? So as a result, this parameter gives us an equation. Delta V equals delta V1 plus delta V2 plus delta V3. And now we just need to massage this equation in order to get capacitances into this formula, into this equation. How? Using the definition of capacitance. C equals Q over delta V. Right? So if you compare this slide with the slide which we discussed at the end of the previous class, the structure of the slide exactly the same. And then when we get to the resistance, equivalent resistance, again, I will keep the same, exactly the same structure of the slide, so that it's like training, right? It's easier to compare and analyze. Okay, so now using this definition of capacitance, we can rewrite this formula in a slightly different way. So we need to get delta V's. All right, so delta V will be Q over C. So delta V1, it's for this, right? Delta V1 will be just Q over C1. And you see, I don't use subscript next to Q because Q's are the same. Right? So I dropped subscripts. So Q over C1, delta V2 Q over C2, It's instead of this. And for delta V 3, it will be, of course, Q over C3. So all these three will be used on the right-hand side of this equation over here. I will replace. But what about delta V over here? Like in the previous slide, okay, at the end of the previous lecture, we will get this information about this parameter from the equivalent circuit. So delta V, again, the rest of the circuit must work in exactly the same way. The total potential difference, right, across the battery, of course, we can find it by using C equivalent in exactly the same way. So delta V across the C equivalent, and again, using this formula for the definition of capacitance. So delta V equals now Q equivalent, which is Q also, right, and divided by C equivalent, right, from that slide. I mean, from that circuit, damn it, from that circuit, right? So now this can be used on the left-hand side. Again, the structure of the slide exactly the same like what we had at the end of the previous lecture. Okay, so now we just plug these ratios Q over C's into this, and as a result, we will end up with that. Of course, Q's can be brutally canceled, and as a result, we get formula, which of course you all familiar with, right? Usually students don't have troubles using these formulas except I was warning in my recitation classes quite often students calculate these reciprocals 1 over C, 1 over C, and then after that they forget to flip, because here it's a 1 over C equivalent. They forget to flip, and as a result they used 1 over C equivalent as C equivalent. Very, very silly mistake. And then when they see that after the exam, kind of like, damn it, how come that I forgot to flip it, take a reciprocal? Very common silly mistake. So be aware of that. Don't make that mistake. Right. So again, so what is important in this slide? This piece of physics, the charges are the same in the equivalent capacitor and capacitors connected in series, and this piece of physics, right? Okay, so that's what we need. It's a barely derivation. It's again, as I said, I keep it because we can discuss physics over here, right? Okay, so after this, there is an example, but I decided that since we already discussed examples in our recitation classes, right? So you know the procedure. Basically, every time you just use this formula and this piece of physics. So you should be able to just look by yourself at the example. It will be in my slides, right? So here's the example. So we have a battery and now 4 capacitors. This, and over there 2. So first idea, you need to simplify this circuit to the simplest possible when you have 1 capacitor across the battery. And you do the simplifications using those formulas, 1 over C's, or C's, right? So that's formulas how we can find equivalent capacitors. Once you find the value of equivalent capacitor, then, of course, you can find the total amount of charge taken from the battery. Sort of like making a crack in the wall, right? So once you find the total amount of charge, then you can start expanding that crack to see the answers, to see the truth. So once you find total amount of charge, like we've done in our recitation classes, right? Now it's longer, more steps. And then you can start using those pieces of physics as a bridge to move back. For example, here in this case, charges are the same, like what we just discussed in the previous slide. Here, potential differences are the same, like in the slide which we discussed in the previous lecture. Then again, charges are the same, like what we discussed in previous slide. And then, using the definition of capacitance, you can reveal pieces of information, right? Again, so as I said, after we discussed simpler example in our recitation class, we get only 3 capacitors. Now 4 capacitors. You should be able to read it and figure out by yourself, right? It's quite straightforward, nicely structured, as I said in the recitation classes. I like the way this book, the author of this book, arranged the problem around this picture. So first you simplify the circuit, and then you start going back, revealing all the necessary information. Okay, so this will be in the in the slides in the Blackboard. And again, yeah, we discussed, and videos to my recitation classes you can see on my YouTube channel, and also links are in the Blackboard. Okay, so that's what left. These are leftovers from the previous lecture, and now new material. It's time to start introducing current. All right, so now it's chapter 27. And because of this, I postponed the homework till Wednesday. So first of all, a model of conduction, right? And now, right, I feel, basically now it's time for me to confess. Kind of, bless me, Father, for I have sinned. I lied to my students. Where did I lie? And did I lie actually or not? You remember when we discussed properties of conductors in electrostatic equilibrium, I told you, if you expose some conductor to some, for example, external electric field, electrons will start running like crazy first. In order to achieve what? In order to make the net electric field inside of the conductor zero, right? And then when they achieve that, I told you they stop running. They get settled, buy a house, get married, and live happily ever after. True. It's truth, but not a complete truth. Not a complete truth. That's where I kind of not lie, but not completely lied. I just didn't reveal the whole truth. And the whole truth is that, because there was no reason for revealing the whole truth back then. You shouldn't overcomplicate stuff. You need to introduce stuff in small portions, in small steps, right? So that's why I partially lied. Right, so what actually happens? Here is the sort of model of a conductor. So you see we have a crystalline structure filled with this red, right? So nuclei, right? And between them, of course, we have cloud of electrons, free electrons, which capable of moving anywhere we want, right? They want, not we want. And, all right, so usually a conductor is at room temperature, or maybe not room temperature, but above 0 Kelvin. And it means that that material has a significant amount of thermal energy. And that thermal energy for electrons is gigantic. And as a result, those electrons has a gigantic amount of, that thermal energy. As a result, they have a very large speed. So they fly still, they fly like crazy, very fast. But they fly not in an empty space. They fly among these nuclei. And for example, let's say follow this over here. You see this line over here, right? So let's try to follow that electron. So first, it travels that way because of that thermal energy. It has gigantic velocity, and sooner or later, it will collide with the nuclei. There are lots of them. Sooner or later, it will definitely collide. Collide, so collision, concussion, recovery, and again, acceleration. Sooner or later, it will meet another nuclei. Again, collision, concussion, recovery. It sounds familiar, right? It sounds like American football, right? I like poking American football because I'm a soccer fan, right? I like soccer, right? So I like poking that direction, right? So then again, after collision, it will fly in a different direction. Again, collision, then again, fly in a different direction. So if you try to follow this electron over some finite period of time, you will see that that electron, although it flies like crazy, very, very fast, but it doesn't leave, for example, a certain volume. So there is no any drift of an electron in any certain direction. So it just bounces around locally. It's like people, even after settling down, some people, they still run around, right, locally. And the same like electrons, right? So there is no a certain drift, and there is no a drift of electrons in any certain direction, right? So of course you can, so that's why I told you, okay, they kind of settle down. But of course, they still fly fast, but only locally. Right? Okay, that's what happens if we don't apply any external potential difference. across a conductor or electric field. So that's what happens. Right? So now let's apply across this conductor a potential difference. Let's attach a battery, for example, right? A source over a constant potential difference. As a result, we're going to see this situation. So you see this electric field, these red lines, electric field, electric field, electric field. As a result, of course, electron will experience force that way, right? So now electrons, they still have these gigantic velocities. Those velocities, they fly very fast. But now, on top of that fast velocity, there is a small drift in a certain direction, in this case, in that direction, in the opposite direction to the direction of the electric field, because we're talking about electrons, negative charges. As a result, you see, instead of these straight lines, blue lines, now we have some sort of like a parabola, small parabolas. So on top of that gigantic velocities, there is a drift of all electrons in a certain direction, in that case, that direction. And that drift, that's what we call the electric current. That drift. And of course, velocity of that drift is much smaller than velocities because of that thermal energy. Right? So that's what we call current. Okay, so we introduced the idea of current on this conceptual way, on sort of using this microscopic picture, right? But of course, since we are all engineers, chemists, physicists, right? So introduction of stuff just on a conceptual level is not good enough. We need to introduce quantities properly using expressions so that we can calculate them, we can get numbers so that we can compare values, so we can predict something, right? So we need an expression. So now we need to introduce idea of current properly, not just on a conceptual level. Right? Okay, and now let's define current properly. Okay, and definition of current is absolutely normal, absolutely logical. Anyone who would try to introduce the idea of current, everyone would be able to introduce in exactly the same way. For example, right, let's imagine just ordinary situation. Let's say you got bored and you go to, watch Boston Marathon, for example. And of course, the best place to watch it, it's at the Heartbreak Hill, because after those 4 hills, runners are completely exhausted, and that's where you can enjoy it the most, see how people suffer, right? All right, and you can sit and sip whatever you liked sipping, right? Okay, let's say you get bored watching that, and you start thinking about physics. It happens occasionally. All right, so, and let's say you want to introduce a current of runners. So what would you do? You would do it something like over here, Garfield. You see some cocktail, right? He's sitting, right? Still breathing. Oh no, in this case, he's not breathing. All right, and so what would you do? You would create sort of like an imaginary line which goes across the road, like a cross-sectional area across the road, and you will look at your watch and start counting runners. Let's say over 10 seconds. You watch over 10 seconds, and let's say you count 50 runners over 10 seconds. Of course, if you take a ratio of number of runners over the time, you will get an average current over 10 seconds. In that case, 50 over 10, it will be 5 runners per second. Electrical current is introduced in exactly the same way. But in this case, in case of electrical current, of course, you're not counting runners. Okay, actually, you can call electrons as runners also. We count electrons crossing some imaginary cross-sectional area. For example, you created let's say this is your wire. You imagine a cross-sectional area, like over here, right? You see the line, Garfield, imagine, right? And start counting electrons crossing that cross-sectional area. But of course, we also know that each electron carries a certain amount of charge, 1.6 times 10 to the power of minus 19. So if let's say 100 electrons cross your imaginary line, take that 100 multiplied by the charge, you will get charge of 1 electron. Of course, you will get the total amount of charge which crossed your imaginary line. And then divide that amount of charge by the observational time, and that will be your current. Exactly the same definition, like if you would, as you would try to introduce the current of runners. Physics is quite logical, and it's very close to our life. Like, of course, quantum mechanics, it's push it over aside, because quantum mechanics, it's a completely strange world, right? Difficult to connect with our world. Right, okay, so now what? As I said, if you have a wire, you imagine a cross-sectional area, it's like over here, this dashed line, right? And start counting charges. Let's say over a period of time dt, this charge, sorry, pressed too hard my flipper. All right, let's say over this period of time dt, these charges, you see dq, these electrons, and of course this charge dq, crossed this cross-sectional area. So you take dq divided by the your time of observation, and that's your current. And of course, if dt is infinitesimally small, you will get an instantaneous current at that particular moment of time. But of course, if you observe over some finite period of time, let's say 10 seconds or 1 minute, of course, you can introduce what is called an average current over that period of time. Right. So of course, if you talk about average current, instead of dq, we can use sometimes just q, because dq, it's infinitesimally small. You can use, in that case, q divided by delta t. Delta t, it's a finite period of time of your observation. Right, okay, so now that's definition of current. And now, so we introduce a new quantity. What about units? Do we have to introduce the special unit? No doubts, the special unit is needed because current is used everywhere. All right, so instead of pronouncing coulombs over seconds, it will be very annoying. If you use every day, millions of people use current, so of course they will hate you if you don't introduce the special unit. They will introduce their own unit to simplify their life. So amperes, units of current, right? Amperes, and of course 1 ampere, it's 1 coulombs over seconds, right? Okay, now let's digress a little bit. You remember in physics 1, how many fundamental units or basic units have you introduced? What do I mean by basic or fundamental? It means that using those units, you can construct any other units. And in physics 1, it was in mechanics. Units to measure mass, kilograms, units to measure length, meters, and units to measure time, seconds. Kilograms, meters, and seconds are basic units, SI units, right, in mechanics. The rest can be constructed out of those three. For example, newtons, it's a kilograms times meters divided by seconds to the power of 2. Any other units, again, can be constructed out of those three. So now, in electricity and magnetism, to that set of fundamental units, we have to add only one additional unit, and that is ampere. Not coulombs, amperes. So now, from now on, we will have kilograms, meters, seconds, and amperes. 4 basic units. Not coulombs. Well, you can ask why not coulombs, why amperes? I guess from the practical point of view, it's easier to measure amperes, not coulombs. Right. Grab ampere, meter, amp meter, right. Done. Right. And then when you take physics 3, or maybe you already took it, right, you will add, which is thermodynamics basically. You will have to add one additional basic unit to that set of units. Kelvin, units of temperature. That's it. So those 5 units, that's the sort of foundation of that SI system. Again, kilograms, meters, seconds, amperes, and then in physics 3, Kelvin, units of temperature. Okay, so I want to digress and emphasize that amps are very important units. Right. Okay, so now we introduced current. So next, direction of current. Of course, we have circuit, right? Closed loop. And of course, current can flow this way, counterclockwise and clockwise. So which direction should we pick? Let's imagine some completely arbitrary circuit. Battery, positive electrode, negative electrode, and some device, some element. It can be a resistor, it can be bulb, it can be motor, it can be anything, just any device. And so now, which direction should we pick? Clockwise or counterclockwise? Usually I ask this question, and of course most of the students know the correct answer. And they tell me, right? But let's pretend that I don't know the correct answer. Basically, let's imagine ourselves living, 200 years ago, approximately, give or take, right? When this stuff was a hot subject, in research, of course, right? And they were investigating, researching these circuits, right? Electricity and magnetism, right? And let's imagine yourself, so now you're at this point and you need to introduce the direction of current. For the first time, right? In the history of mankind. So, me, if I would imagine myself, right, I would think this way, and I think it's completely logical, right? Look, which charges actually travel in the circuit? Electrons. Positive charges, they don't travel. Positive charges are those nuclei, crystalline structure in this wire, right, and in the elements. So positive charges, they don't travel. So, and of course, electrons travel from which way? Of course, they travel from minus. That's the negative electrode is filled with electrons, right? And of course, they travel from minus to plus electrons. So actual flow of electrons this way. And I would think this way, okay, so since these guys travel, so let's use that direction as the current direction. Why not? It looks completely logical for me. I don't see any troubles with the logic, which I just told you, right? But it's logical, it's great, but very often logical is not the best way. Now let's look from the practical point of view, from the point of view when you start working with this. Let's recall, where else have we seen any directions? You remember, like in the third lecture, so we introduced electric field lines. And what was the direction of electric field lines? Since we use the positive probe charge, so electric field lines, all the time they start on positive charges and end on negative charges, right? Every time from plus to minus, right? You remember, right? So now let's imagine, so we choose here direction of current from minus to plus. So now as a result, you have to think every time. Electric field from plus to minus, current from minus to plus, plus minus, minus plus, plus. Sooner or later, your brain will start skipping a bit, right? And you will start getting confused occasionally. Not all the time, but it's normal. It's absolutely normal, right? So it's not good. So in order to avoid those troubles, it's better to follow exactly the same convention. For example, like electric field lines from plus to minus. And as a result, let's also here pick a direction of current from plus to minus. So the pattern will be exactly the same. The convention is exactly the same. So if you wake me up in the middle of the night, of course I will be very grumpy, but I will be able to tell you what you want to know the direction, whatever direction, from plus to minus, give me a break. To avoid any troubles, it's much more practical to follow the same convention. Easier to make your life in the research, right, in engineering work, easier. From plus to minus. Whatever direction, from plus to minus. All right? So that's the logic. Why? By convention, electric current from plus to minus. It's a motion basically of positive particles, which of course do not travel. But of course, from the mathematical point of view, a motion of negative charges this way, from mathematical point, is the same as motion of positive charges that way. Although, of course, in real life, positive charges do not move. All right. Okay, so that's the logic of why current is from plus to minus. Kind of not completely logical, that's why I put this picture, right? It's not logical, it's just our policy. Right. So that's the direction of current, from plus to minus. The same like electric field lines, from plus to minus, whatever direction, from plus to minus. Right. Okay, so that's direction of current. And now, what else? Now let's introduce the current density. All right. Okay, that's just a picture. Might be useful. I just took it from the book. Okay, this is not, I don't want to poll this, right? So quite simple. Let's assume that we have a wire. And you see, now we know that every minute 120 coulombs of charge crosses this cross-sectional area, right? And you see now definition of current, Q over delta T, because right now we cannot talk about instantaneous current. We can talk about the average current, because observational time, what? A minute, 60 seconds, right? So that's why we use Q over delta T, not dQ over dt. Right? Okay, so what's the current in this case? And sort of the catch, but of course very weak catch in this problem, don't forget to convert to seconds. Don't use any, okay, not weird, but wrong units, right? Seconds, because amperes, it's a coulombs per seconds. Don't use minutes, right? But usually, again, as I said, students don't have troubles with that. So in this case, 120 coulombs divided by 60 seconds, not 1 minute, 60 seconds, because amperes, coulombs over seconds. Right? And of course, in this case, 2 amps of current. Right? Okay, it's not that complicated, right? So that's why I don't want to poll it. So in this case, 2 amps, right? I don't think that you need more explanations of that. All right, so now next, current density. And it's a very important quantity, not as important as current, but when we get to Ampere's law in a couple of classes, you will see that you will have to use that a lot. And students struggle a lot, like with charge density in the Gauss's law. Then we will have to use this in Ampere's law. All right. Okay, definition is quite simple. Let's assume that we have a wire. You see the wire. Current flows that way, let's assume. Cross-sectional area you picked in order to measure the current, right? And let's say this is the amount of charge crossing this cross-sectional area in the period of time. Of course, you can calculate current. And so, by definition, current density, you just need to take current and divided it by the cross-sectional area through which that current flows. Very simple, just I divided by A. Of course, current units of current, just whatever you see in the formula. Amps divided by square meters. Of course, there is no point of introducing the special unit for this case. It is used quite often, but directly related to amps, amperes, so it doesn't make sense to introduce the special unit. All right, okay, it will be used a lot. All right, so next. So we introduce current, then current density. Oh, no. First current, then direction of current, now current density, and next, conservation of current. Conservation of current, right? And what is behind conservation of current? It's a conservation of charge. It's just conservation of charge applied in circuitry. We call it conservation of current. And we're going to have two sort of parts of that. So first one, if you have a wire without a junction point. No, software removes that. You don't see it. So if you have a wire without any junction point, right? So in this case, if you don't have junction point, it doesn't matter where you measure your current. Here, cross-sectional area, if you pick here, 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 or even if you have a different cross-sectional areas like this, right? So you see here a larger diameter, here a smaller diameter. It doesn't matter where you take this cross-sectional area, this, current will be the same. Analogy, direct analogy with water, because water is difficult to compress. As a result, if you have a pipe of this cross-sectional area, right? So here a smaller cross-sectional area, here a larger, right? Over here, where the cross-sectional is smaller, of course, water will flow faster, all right? And let's say you measure amount of water crossing per unit time. Let's say you measured 5 liters per second. When you measure that water per unit time over here, of course, now cross-sectional area is larger. Of course, water will flow slower. But because of the larger cross-sectional area, you can get exactly the same 5 liters per second. Right? The same with current. It doesn't matter what's the cross-sectional, how big cross-sectional area is, or what's the shape of the cross-sectional area. Current is the same. Again, if you don't have any junction points. Right? I will emphasize on that many times, right? So if you don't have junction points, current is the same. Or for example, if your wire is curved, for example, again, it doesn't matter which cross-sectional area you pick to measure current, current will be the same. Right? Okay, so that's if you don't have a junction point. But what if you do have a junction point? What is junction point? So if you have a wire, right, and over here somewhere you soldered another wire. So this is a junction point, right? Because over here current can get split, right? Can be splitted, right? Can be splitted, right? So as a result, this is a junction point. Right? So what is the story if you have a junction point? Completely logical. The total amount of current entering junction point must be equal to the total amount of current leaving. Electrons cannot just park somewhere in a junction point and take a rest, right? No. If they were pushed in the junction point, they will be also pushed out of the junction point. No parking and taking a rest somewhere, right? So the total amount of current entering in a junction point must be equal to the total amount of current leaving junction point. For example, like let's say this is a junction point, right? And we have one wire with current entering and these two wires with currents leaving. So let's say this is I in, this is I out 1, and this is I out 2. So in this case, I in equals to I out 1 plus I out 2. Very straightforward, right? And again, what is behind of all this? Conservation of charge applied for circuitry, in a circuitry. Okay, so now we introduce current, direction of current, current density, conservation of current. Now probably it's time for a question, and we have a couple of minutes, right? And of course, in a couple of classes, we will use it as a Kirchhoff rule, loop rule, or a junction rule, sorry. Right, click a question. We have a junction point, you see. Oh, and for this question, yes, in the chat, there is a poll. Again, use the poll in the chat, not, don't send the answer through the chat. Use the poll in the chat. And I can see it on my screen. Okay, so we have junction point and 4 wires soldered at this point. We know that 2 amps of current entering junction point, you see, through this wire. We also know that 5 amps of current entering the junction point. We also know that 9 amps of current leaving the junction point. But we have nothing, we don't have any information about this 4th wire. So you need to answer, what's the amount of current flows through this 4th wire, and what's the direction? Is the current flowing that way, which is to the right or to the left? Right? Every time I have to turn myself, because again, as I said, I need there is a TV, big TV in front of me in order to use green screen effect, right? And it flips me. Okay, so again, the poll is in the chat. Try to answer, and then I will discuss it quickly, and then we will call it a day. Maybe I will hold you like 1 extra minute, because I don't want to leave this question for the next class, to the next class. Yeah, no, you know that. You don't need. My God, some of you already answered the second question. We didn't even get to the second question, right? And some people already answered. It looks like some people are not even following, right? So what is happening in the class? It's Okay, so most of you believe in D. Okay.
Is this part of our attendance grade? Because
No,
sometimes I
no,
don't see them.
no, no, no. I use
Okay.
that as an attendance during our normal semester, right, when we are at school. But now, since we cannot use clickers, right, so I don't use that as an attendance. I use the code as an attendance.
Okay, thanks.
To check an attendance.
About the attendance, what happens if we say we attend the lectures, but we accidentally forget to log a code?
Oh, it happens, but so next time, try not to forget.
Okay.
Okay, once you can send me email, right? I can sort of fix it manually at the end of the semester. But if you start sending me every time, right? Of course, I wouldn't be happy completely, right?
Thank you.
Okay, guys, right? It looks like most of you believe in. Okay, let me discuss it quickly. So the reasoning is this. Of course, we need to let me click on slides. All right, so we need to use conservation of current. I saw a distribution of answers, right? Okay, total amount of current in must be equal to the total amount of current out. So we don't know anything what happens to this current in the fourth wire. So, and in order to apply this law, conservation of charge properly, let's assume a direction of current in the fourth wire. Why can we assume it? Because we have 50% chances of getting it right. It's a gigantic probability, right? So it either to the left or to the right. Let's assume a certain direction. Of course, I don't know if my assumptions are going to be right or wrong. But if I assume a direction, I can write this equation properly. And if after my calculations, my current will be positive, then what? It means I'm lucky. So it means that my assumption about current direction was correct. But if my answer will be negative, okay, what a big deal. I know the number, and minus just indicates that my original assumption about the current direction was wrong. So make a statement. So current actually flows in the opposite direction. We're going to use that trick often from now on. Since, again, every time current, it's either this way or this way, clockwise, counterclockwise, we're going to assume current directions quite often. And at the end of the calculations, every time we can adjust the direction. So let's do the same here. I assume that Ix in the fourth wire is out, which means that way. Okay, and with that assumption, out current is 9 amps and that unknown current. This current in, this current in. So as a result, I will have 2 amps in, 5 amps in, it's this side. Out, 9 amps we know, and my assumed direction I sub x. Okay, so now if you solve it for I sub x, obviously you will get -2. It means what? Of course, the absolute value, the value of the current is 2 amps, and minus just tells me that I was not lucky, that my assumption about the current direction was wrong. So current actually flows not out, but into the junction point. But again, I solved the problem, so who cares that I was not lucky in my assumptions? We're going to use that trick often, right, about assuming the current direction. Okay, I wanted to finish discussing this, right? And now the system can be more complicated. You can have, I don't know, 125 currents, right? But still using this trick, you can solve that easily. Right? Okay, occasionally I give questions like this on the exams among multiple choice questions. Right? It's a quick calculations, doesn't take much time. Okay, sorry for holding you a few minutes, right? Okay, if you have questions, you can ask. Otherwise, I will see you next week. Again, it's a long weekend. Monday is the holiday, and on Tuesday, we're going to have, I think, Monday's schedule. Right?
Higher in the sky, the Olympic flame glows like the sun. Watching